Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from an Introduction to Mechanics by Klepner and Kolenko. We will continue to discuss topics from Chapter 6, Angular Momentum and Fixed Axis Rotation. In today's class, let's analyze the dynamics of pure rotation, and you will find that this is going to be very similar to the analysis of a simple translation motion. Now, so far we have seen that the motion of a system of particles is simple to describe if we distinguish between external forces and internal forces acting on the particle. Why? Because by Newton's third law, the internal forces cancel and the momentum change of the system happens only because of the external force. Okay, that's how we came to know about one of the most fundamental principles in classical mechanics, which is the conservation of linear momentum, where we have seen that when the total external force acting on the system is zero, its momentum remains a constant, or momentum of an isolated system is conserved. Now we can follow this same procedure to describe rotational motion. So here also we are going to distinguish between external and internal torques. Remember, instead of force in angular motion you have torque. Okay, so we have external and internal torques, and by the end of this module you will find that the angular momentum change of a system happens only because of the external torque, because just like internal forces, the internal torques also cancel, and from this you can derive a very important principle known as conservation of angular momentum. Okay, now in today's discussion we are going to talk about a special type of fixed axis rotation known as pure rotation, where the axis of rotation is at rest, like the rotating door shown in this video. Here you can see the axis of the rotation it remains at rest, or if you look at a rotating fan, the axis is always at rest. Okay, so consider a body rotating with angular velocity omega about the z-axis. Then the z component of angular momentum is given in terms of its moment of inertia as Lz equal to I omega, and we know that the rate of change of angular momentum is a torque. So torque in the z direction tau z equal to d by dt of I omega. I is a constant, take it outside the derivative, so this is I into d omega by dt. Rate of change of angular velocity is nothing but angular acceleration alpha, so tau z equal to I alpha. Since we are concerned with rotation only about the z-axis, we can get rid of the subscript z and write down a general equation, torque tau equal to I alpha. So we can extend this to calculate the kinetic energy of a body undergoing pure rotation. So if you imagine that the rigid body is made up of a number of particles, you can find kinetic energy of each particle, take the summation of that, you get the total kinetic energy. So I can write total kinetic energy K equal to summation over J half mj Vj square. In the previous class we have seen that there is a relation between linear velocity and angular velocity. Linear velocity is given by rho multiplied by angular velocity, where rho is the perpendicular distance from the axis. So I can write Vj equal to rho j omega. So instead of Vj I substitute this, so my equation becomes K equal to half summation over J half mj rho j square omega square. In the last class we have seen summation over j mj rho j square is nothing but the moment of inertia I, so K equal to half I omega square. Now if you compare a translation motion or a linear motion and pure rotation, you will find that they are almost similar. If you replace all the linear parameters with the corresponding angular parameters, you get all the equations getting translated from linear motion to the pure rotation. Let's see how does this happen. In the case of translation motion, the most important, most fundamental parameter is the position vector or displacement r. In the case of pure rotation, the fundamental parameter is the angular displacement theta. Now dr by dt, rate of change of position, gives you linear velocity v. Same way d theta by dt gives you angular velocity omega. dv by dt gives you linear acceleration a. d omega by dt gives you angular acceleration alpha. In translation motion, you have mass. The equivalent parameter in the case of rotational motion is moment of inertia. But there is a slight difference between these two. Mass depends only on the amount of substance in a system, whereas moment of inertia depends on the amount of substance as well as its distribution. Now, mass into linear velocity gives you linear momentum. If you want to get the corresponding equation in pure rotation, simply replace all these linear parameters with corresponding angular parameters. So instead of m, you have I. Instead of v, you have angular velocity omega. Instead of linear momentum p, you have angular momentum L. So L equal to I omega, right? So it's almost an extension of translation motion. And the equation of motion in translation is F is equal to ma. Same way, you replace all the parameters with corresponding angular terms. Instead of F, you have tau, torque. Instead of mass, you have moment of inertia I. Instead of linear acceleration, you have angular acceleration alpha. So tau equal to I alpha. So this is the equation of motion in rotational, in the case of pure rotation. Kinetic energy K equal to half mv square in the case of linear motion. Instead of m, you have once again I. Instead of v, you have angular velocity omega. So you get K equal to I omega square. So the method of handling problems involving pure rotation under applied torques is a straightforward extension of the familiar procedure for treating translational motion under applied forces. I can illustrate this with a practical example. An Atwood machine with a massive pulley. So this is an Atwood machine. So there is a central pulley and there are two masses m1 and m2. So if m1 is greater than m2, m1 is going to come down and m2 is going to go up. Since these two are connected, acceleration is the same, just that the direction of acceleration is downwards on the m1 side and upwards in the m2 side. Okay, so m1 and m2 are undergoing a translation motion or a linear motion. But look at the pulley. Pulley is going to rotate, right? So it's and the axis of the pulley is fixed. The axle is fixed to the top surface. So this is a pure rotation. If I take alpha as the angular acceleration, then I can write down the equation of motion for both the masses as well as the pulley. Okay. So as I said, the pulley undergoes pure rotation about its axle. So we take the axis of rotation to be the axle. Now our aim is to find out what is the acceleration of this system, the linear acceleration of the system. Okay. So as always, first you need to identify what are the various forces acting on the system. Then you draw the force diagram. Okay. So in the force diagram, you replace the objects with point masses. So I have point mass m1 here. And what are the forces acting on it? There is weight which always acts in the downward direction. So W1 downwards. And it hangs by a thread. So there is a tension T1 acting in the upward direction. And of course, the overall acceleration A is in the downward direction because M1 is heavier than M2. In the case of M2, weight to W2 is acting downwards, tension T2 is acting upwards, and the net acceleration A is in the upward direction. And what about the pulley? So pulley has its own weight given by the mass MP. So the corresponding weight is going to act downward. So WP is going to act downward. And it's fixed onto this surface, so there is an upward normal force N acting in the upward direction. and it's undergoing a rotational motion. So on the right side there is force T2, so you have a force corresponding to T2, and on the left side you have tension T1, so there is going to be a torque corresponding to T1. Okay. Now let's write down the equation of motion for both the masses as well as the pulley. So for M1 I can write T1 minus W1 equal to mass into acceleration M1 into A. A is in the downward direction, so this is minus M1 into A. So if you multiply both the left and right hand sides with minus 1, you get W1 minus T1 equal to M1A. For M2, T2 minus W2 equal to M2A. Now what about the pulley? So we need to write down the equation of motion in terms of torque. So as I said, since there are two forces, I have two torque. First, what is the torque on the left side? This is R cross T1. When you do that, you find that the direction is out of the plane, which you take as the positive direction. Since R and T1 are perpendicular, the cross product is replaced by a normal product of corresponding magnitudes. So on the left hand side I have T1R plus T1R. On the right hand side the direction is into the page, which you take as the negative direction, so we have minus T2R. So this is the total moment of force, which is equal to, since alpha is the angular acceleration, I can write the torque as I into alpha, where I is the moment of inertia of this rotating disc. Okay. Now if you want, you can write another equation of motion. Since you have a normal force in the upward direction, I can write N minus WP minus T1 minus T2. This is equal to 0. So this equation is actually trivial. It only means that the total upward force N is balanced by the total downward force, so that the pulley or the axle is stationary, which is like common sense, right? I can also write down a constraint equation connecting angular acceleration alpha and linear acceleration A, because we know that the entire system is connected through a rope, right? So as long as the rope doesn't slip, the velocity of the rope is nothing but velocity of a point on the surface of the V. Okay, so let's say velocity V equal to omega into R, where R is the radius of the pulley, omega is the angular velocity. Okay. From this I take derivative on either side. dV by dt is linear acceleration A. R is a constant, so the derivative on the right side is R into d omega by dt. d omega by dt is angular acceleration alpha, so I can write A equal to alpha R. So just like linear velocity is angular velocity multiplied by the radius, linear acceleration is going to be angular acceleration multiplied by the perpendicular distance or radius. Okay. So once I have all this information, I can solve the equation of motion and find out what is the value of A. So I am going to add these two equations. So W1 minus T1 plus T2 minus W2 equal to M1A plus M2A. When I rearrange the terms, I can write W1 minus W2 minus T1 minus T2 equal to M1 plus M2 into A. Now from the third equation, I can write T1 minus T2 equal to I alpha by R, but alpha equal to A by R. So I can write T1 minus T2 equal to IA by R square. Now in this equation, substitute for T1 minus T2, I get W1 minus W2 minus IA by R square equal to M1 plus M2 into A. From this I can write A equal to W1 minus W2 divided by M1 plus M2 plus I by R square. weight W is nothing but mass into acceleration due to gravity. So W1 is m1g, W2 equal to m2g. So in terms of masses, I can write A equal to m1 minus m2 into g divided by m1 plus m2 plus I by r square. Now let's calculate the expression for moment of inertia. So if you assume that the pulley is a simple disk with mass m and radius r, the moment of inertia is half mpr square. So substitute for I in this equation, you get A equal to m1 minus m2 into g divided by m1 plus m2 plus mp by 2. So you can note that the analysis is very similar to the case of translation motion. You write down the equation of motion and you know all the equations connecting linear and angular parameters, so you do appropriate conversion and arrive at your result. And in particular, if you look at this result, you find that when you look at the denominator, you find that the mass of object 1 and mass of object 2, these two are completely applied here, but the mass of the pulley, it's not completely applied, only the half is applied. So even though the pulley increases the total initial mass of the system, in comparison with the hanging weights, the effective mass of the pulley is only half its original mass. Let's look at some other common examples of physical systems executing pure rotation. The most important one is a simple pendulum. So as we know, simple pendulum is a simple harmonic oscillator, which is a very important mathematical model used throughout in physics. So I'm sure all of you are familiar with simple pendulum in your +2 classes. So it's a system consisting of a small heavy metallic bob which is suspended from a rigid support using a thin flexible massless string. Okay. So suppose m is the mass of the bob, metallic bob, and L is the length of the wire or the string. So the dotted line is the equilibrium position. So when there is no force acting on the system, so this is where the bob is going to reside. But when you apply a force, suppose you pull it to one side and release it, about this equilibrium position, it's going to oscillate. Okay, and the oscillations are simple harmonic. Okay. So we are going to monitor the angular displacement phi as a function of time. So at one particular time, this is the position of the bob. So since this angle is this length is L, this angle is alpha, this perpendicular distance is L sine alpha. Now let's draw the force diagram at this particular point. There are two forces acting. One, of course, the weight, which always acts in the downward direction. And since this metallic bob hangs by a thread, there is a tension T acting along the thread in the upward direction. Okay. Now at this point, the moment of force about the point of suspension. So one thing before that, this is a pure rotation because the point of suspension is stationary. So the entire oscillation happens about the stationary point of suspension. So this is a pure rotation. Now let's calculate the moment of force about the point of suspension. So moment of force is nothing but force multiplied by perpendicular distance. So force is mg, perpendicular distance is L sine alpha. Since mg is acting in the downward direction, I have a minus sign here, so this is minus mg L sine alpha. And what about the moment of inertia? This is a single particle system, so moment of inertia is nothing but mass into square of the distance from the point of suspension. So this is m into L square. And angular acceleration alpha is nothing but d square phi by dt square. Okay. Now I can write down the equation of motion. The equation of motion is nothing but torque tau equal to I alpha. Instead of alpha, I can write I into phi double dot. And I know the expression for moment of force. Moment of force is nothing but the torque. So I can write I alpha double dot equal to minus mgl sine alpha. I is ml square, so ml square phi double dot equal to minus mgl sine alpha. M is common on either side, cancel that and take the term on the right hand side to the left. So you have L phi double dot plus g sine alpha equal to 0. So this is the equation of motion. Now what we are going to do is we will try to bring it to a standard equation, the equation of motion of a simple harmonic oscillator. Why do we do that? Because we know how to solve the equation of motion of a simple harmonic oscillator. Or even if you don't solve it explicitly, you know the standard form of the solution in the case of simple harmonic motion. So we try to bring this equation of motion to the standard form of a simple harmonic motion. Okay. Now, for that, we are going to use a mathematical tool known as Taylor series expansion. Now, I am not going into the details of the Taylor series generation. Probably you will learn it in one of your mathematics courses. So just know that any function you can approximate it to an infinite summation or a series summation having infinite number of terms. Okay. Now the Taylor series expansion for sine function is given as sine phi equal to phi minus phi cube by 3 factorial plus phi to the power 5 by 5 factorial minus phi to the power 7 by 7 factorial all the way to infinity. So basically you have only the odd powers in the summation. Now here, if the value of phi is very small, then I can make a simplification. Suppose phi is 0.1 radians. Okay. So if phi is 0.1, phi cube is going to be 0.001. Phi to the power 5 is 0.00001. So basically compared to phi, all the higher orders are going to be much smaller. So for all practical purpose, you can neglect all these higher order terms and approximate sine phi to phi. So when phi is small, sine phi is same as phi. So now take it to the physical system. What's the meaning of phi being small? Your simple pendulum has very small oscillation. So under small oscillations, I can approximate sine phi to phi. So my equation of motion becomes L phi double dot plus G phi equal to 0. Now divide this entire equation with L. So phi double dot plus G by L phi equal to 0. Now if you call this term G by L as omega square, then you get the standard equation of a simple harmonic oscillator, d square phi by dt square plus omega square phi equal to 0. Where omega is the angular frequency of the harmonic oscillator, and in this particular case omega is given by square root of G by L. Now what is the advantage of approximating your system to a simple harmonic oscillator? Because as I said, in the case of simple harmonic motion, the standard form of the equation is known. Even without solving it, I can write down the solution. Phi equal to a sine omega t plus b cos omega t, where a and b are unknown constants. And we know how to find the values of unknown constant, right? Since this is a time dependent equation, you have to use an initial condition. So assume that I start this motion from one of the endpoints. Okay, when time t equal to 0, I'm going to pull it to the right side, the extreme right side, then I release it. Okay. So at the extreme right side, let me say the angular displacement is phi naught. So with respect to equilibrium position, the angular displacement is phi naught. So this is my initial condition. At time t equal to 0, phi equal to phi naught. Using this information, you can calculate the values of the constants. So substitute in this equation. So phi naught equal to a sine omega t. Now t equal to 0, sine 0 equal to 0. So the first term vanishes. In the second term, cos 0 equal to 1. So you have phi naught equal to b. So you found the value of b here, and a is equal to 0. So your solution is going to be phi equal to phi naught cos omega t. So when you plot that, you get this kind of a graph. So you can see that there is a periodic variation in the value of the angular displacement. So this is nothing but a sinusoidal variation. So that's why we call it as a simple harmonic motion, right? Because this is the fundamental characteristic of any simple harmonic motion. The solution is going to be sinusoidal. Now, as you can see, the motion is periodic. The same waveform is repeating again and again. So the motion is going to repeat periodically over the entire time frame. And the time taken for one complete cycle is known as time period capital T, which is also the time between successive repetitions of the motion. Now let's find out an expression for time period. Time period, from its very definition, is nothing but the inverse of frequency. So if I call f as linear frequency, t equal to 1 over f, and linear frequency is nothing but angular frequency omega divided by 2 pi. So I can write t equal to 2 pi by omega. I know the expression for omega, so substitute for that. I get t equal to 2 pi divided by square root of g by L, or t equal to 2 pi square root of L by g. Now phi naught, as I said, this is the maximum amplitude. So in normal terminology, it's simply called as the amplitude of the motion. And as you can see from this expression, the time period is independent of the amplitude of motion, because it depends only on L and G. And that's why the pendulum is so well suited for regulating the rate of a clock. Okay. Let's do a simple problem. What is the change in time period of a simple pendulum when its mass is doubled and length is halved? So look at the equation, t equal to 2 pi root L by g. So mass is nowhere featured. So doubling of the mass is not going to affect the time period. So this is the first information. So this part is given just to confuse you. Okay. So time period depends only on length, and length is in the numerator, which means when length increases, time period is going to increase. When length decreases, time period is going to decrease. Okay, so from this equation you can calculate how much percentage of change happens in the time period. Now, simple pendulum is a system which you would have probably seen only in your labs. In our daily lives, we don't actually encounter a simple pendulum. But we encounter systems which behaves like a simple pendulum, or behaves like a simple harmonic oscillator. Like suppose an object like this which hangs on an axle. If you apply a force, it is going to oscillate about this center point, right? So this is like a simple harmonic oscillator. So any hanging object which oscillates in a manner similar to a simple pendulum can be treated as a physical pendulum. So using the fundamental understanding of pure rotation, we can analyze the motion of a physical pendulum now. Okay. Now, one thing, the swinging object can have any shape, because in the equation of motion, shape doesn't feature. We are only bothered about its mass. So let's say the center of mass is at a distance L from the pivot, which is nothing but the point of oscillation. And the motion is pure rotation about the pivot, and the moment of inertia about the pivot, I call it as IA. Now, choosing the axis of rotation through the pivot, we find that only torque acting in the system is the torque due to gravity. And we know the expression for torque due to gravity. This is nothing but the weight multiplied by the corresponding perpendicular length. Okay. So if you look at the force diagram of the center of mass, so the weight of the system acting in the downward direction, and you need to calculate the torque corresponding to this particular configuration. So this length is L, so if I call this particular angle as phi, then this perpendicular distance is L phi, so the total torque is going to be L sine phi W. Since W is acting in the downward direction, which is the negative direction, you have to add a negative sign. So minus LW sine phi is the torque. And in terms of the angle phi, I can write it as moment of inertia Ia multiplied by phi double dot. So this is the equation of motion. Now I can simplify this. So if I assume that the angle of oscillation is very small, then I can approximate sine phi to phi. So the equation of motion becomes Ia phi dot plus LW phi equal to 0. Now weight W is nothing but mass m into acceleration due to gravity g. So the equation of motion becomes Ia phi double dot plus mlg phi equal to 0, or phi double dot plus mlg by Ia into phi equal to 0. Now if I call this coefficient as omega square, I get d square phi by dt square plus omega square phi equal to 0, which is nothing but a standard equation of a simple harmonic oscillator, where omega is the angular frequency given by square root of mlg divided by Ia. And I know the standard form of the solution, phi equal to a cos omega t plus b sine omega t. Now we can write this result in a simpler form if we introduce the concept of radius of gyration. Now radius of gyration is a concept similar to center of mass. Remember the motivation behind the center of mass. You have a multi-particle system. So if you try to analyze the motion of each of the individual particles, this is going to be a very tedious task because you will have to write down n equations of motion. So you approximate the multi-particle system to a single particle system. So assume that the entire mass of the system is concentrated at a single point, and when you apply an external force, this point would behave the same way as the entire system would behave under the same force. Okay. So a many body problem, you simplify to a single body problem. Now same is the case with the radius of gyration. The only difference is that instead of linear motion discussed before, now you have an angular motion. Okay, so you have a multi-particle system. So instead of analyzing the angular motion of each of these particles, you will find a particular point where the entire mass of the system is concentrated, and this particular point is at a particular distance from the axis of rotation. Now the speciality of this distance is that at this distance this single point would rotate in such a way that its moment of inertia is exactly same as the moment of inertia of this multi-particle system about the same axis. And this distance is known as radius of gyration. So radius of gyration helps you to reduce a many body problem to a single body problem in the context of angular motion. So this makes your analysis a lot simpler. Okay. So if the moment of inertia of an object about its center of mass is I naught, then the radius of gyration k is defined as k equal to square root of I naught by m, or I naught equal to mk square. Now from the equations of some of the simple objects we have done in the previous class, we can find out radius of gyration of some of the well-known structures. So in the case of a hoop of radius r, I know that moment of inertia is nothing but mr square. So mk square equal to mr square. So radius of gyration k is nothing but radius of the hoop r. And in the case of a disk of radius r, I know the moment of inertia about the center is half mr square. So when you write mk square equal to half mr square, you get radius of gyration k equal to square root of half into r. Same way in the case of a sphere of radius r, you will find k equal to square root of 2 by 5 into r. Now from the parallel axis theorem, we know that IA equal to I naught plus ML square, but I naught is MK square, so IA equal to M into K square plus L square. Now from this, I can give a nice form to this equation. So in this equation, substitute for IA, so you get angular frequency omega in the case of a physical pendulum is square root of GL divided by K square plus H square. So this is the most generic equation, and the simple pendulum is a special case where the radius of gyration K equal to 0. So you can see when you get K to 0, you get omega equal to square root of G by L, which is what we have derived in the previous case. So that's for today. Thank you.